Hello, my name is Rubina Sheikh. I will be presenting today on Foundries and the next generation of 3D transistors. Here's the brief outline of the topics I will be covering. Introduction, Moore's Law, Intel's innovation in 3D transistor chip process, hybrid approach adopted by others, challenges, future advancement, Foundries' role in developing and advancing this technology, and in the last, conclusion. Introduction. We know that the current chips use two-dimensional transistor of flat architecture. In May 2011, Intel became the first chip manufacturer which announced the development of its new 3D transistor of computer chip at the 22 nanometer level. Intel called it Tri-Gate, and the common industry name is FinFET. FinFETs control current between the source and drain more effectively by surrounding the transistor channel with the gate on three sides. One key benefit of a 3D transistor technology is the super low power attributes and the faster processing capabilities. Intel is producing the new 3D transistors in own factories, acting as both the lab and fab. Taiwan Semiconductor Manufacturer Corporation, Global Foundries, Samsung and other competitors are eager to get their version of 3D transistor chip in the market to their customers by 2014. Now talk about the Moore's Law. Chip manufacture technology follows Moore's Law that has driven the chip industry for decades. Gordon Moore in 1965 made observation that the number of devices on the chip double every 2 years. Each time the minimum metal line would reduce, a new technology node is introduced. Example of the technology generations are 65 nanometer, 45 nanometer, 22 nanometer and so on. This practice of the periodic size reduction is a scaling. One of the key benefits of the introduce a new technology node is that the circuit size is reduced by 50%, doubling the number of the circuit on each wafer. This reduces the cost per circuit significantly, which then driven down the cost of the ICs. Intel innovation. With the development of its 3D 22 nanometer transistor of the computer chip, Intel has gained 2 to 3 years lead over its competitors. Intel described its 3D technology as replacing traditional flat two-dimensional planar gate with a three-dimensional silicon fin that rise up vertically from the silicon substrate. Control of current is accomplished by implementing a gate on each of the three sides of the fin, two on each side and one across the top. Since FinFETs are built on the foundation of the high-K metal gate technology in a leakage reduction, and development of the 3D transistor is a significant step forward in that direction. Intel plans to release the transistors in smartphones and tablets in 2014 to compete against Foundries customers. Hybrid approach. After falling behind Intel, the world's biggest foundries are all gearing up to produce these cutting-edge switches. And to speed up the process, some are taking hybrid approach by combining the new transistor with the older approach to building the wiring that ties them together on chip. This approach will replace the planar transistor with the denser array of the FinFET, but will not advance the manufacture process. It's likely to reduce the production time by 1 year, and Foundries will make 3D transistor available by 2014. In FinFET provide bigger performance gain than shrinking the ordinary planar transistor. Leading foundries adopting hybrid approach include Global Foundries and TSMC among others. Global Foundries say that the key advantage of hybrid approach will be to implement as incremental plans to keep 7,000 design rule already developed for a 20 nanometer planar chip, and change about 60 design rules that are only needed to describe the fin. However, there are some disadvantages associated with this approach as well. This hybrid design will still produce more transistors in array that won't be connected and used. The chip size will not be smaller than the current 20 nano generation in production now, and production on the single wafer cannot be increased, meaning production cost will not reduce. Nonetheless, Global Foundries accept a new chip will be 55% faster and use 40% power than the 20 nanometer generation. Challenges. Chip manufacturers agree FinFET are a huge challenge for the whole industry Major challenges are overhauling computer code for chips so processor operation can be simulated in a realistic time frame. FinFETs stronger electrical effects on their neighbors and have dimensions that cannot be adjusted. There are more risk and the cost in a changing rate already established and proven planar technologies by adding complexity that are not fin-related. Some industry experts estimate a cost of the 6 billion to foundries to develop the manufacturing process and the tools needed for producing next generation of 3D transistor chip. Lithography is another major challenge in making transistors small. To overcome lithography challenge, use of EUV with the multi-patterning are some of the options being pursued by chip manufacturers. However, EUV lithography and carbon nanotubes are still far beyond the reach of the chip designer, forcing them to exert more performance architecture innovation of the 28 nanometer process. Lithography costs are also expected to rise sharply beyond 28 nanometer node, deterring chips companies from moving forward aggressively for a while. Researchers have to continue to invent new structure and material to allow features size scaling. Future advancement. Intel is working on producing a 14 nanometer chip, as shown in the figure, which will be the primaries for smartphones and tablets for the 2014. New chips can cut the thermal design power by 25%. Use of nanowire is another significant advancement towards producing 3D transistor and chip. The figure shows a new design where the transistor channel is made up of an array of the vertically nanowires. The gates surrounding all the nanowires, which improve its ability to control the flow of current. Platinum base source and drain contact sit at the top and the bottom of the nanowires. "3D stacked die. The advantages of the handheld devices where form factor are key and the power levels are low but not suitable for the desktop, laptop and server applications. The figure shows TSV stack chips connecting one chip to another with copper lines that go straight through the silicon, packing many more connections side by side using much slimmer wires. In the projected that TSV will cut power consumption in half, increasing bandwidth by the factor of 8 and shrinking memory stock by 35%. Intel is also pursuing innovation of the new structure and materials to allow for feature size scaling. Another avenue to improve performance is driving down interconnected capacitance by using lower K dielectrics. The most notable achievement might be the simple stacking configuration that's often called 2.5D. This approach builds upon TSVs by running them through an intermediate layer of silicon called an interposer, which sits between IC and a PC board, and placing chips right next to the one another, also in the saving space and power. Global Foundries plans to launch 40 nanometer XM, which will offer performance and power benefits of 3D FinFET, but will be truly optimized for mobile system-on-chip designs, providing a complete product solution up to the system level. Foundries have a very important role to play in advancing the 3D technology. As the 3D transistor are the new reality, world's leading foundries are working aggressively to develop and produce this new 3D design to its customer around the world. Foundries are investing in producing TSV chips while trying to keep chip manufacture costs the same. Intel is pushing the envelope by pursuing an integrated device manufacture concept and become the lab to fab provider. World's other foundries are coming together at a common platform. They are like IBM, Samsung, Global Foundries, and developing the next generation of the 3D transistor and chip. Foundries see their role in advancing the technology rapidly by the forging partnership with chip manufacturers and product manufacturers to create a win-win situation for all. Foundries can leverage their role by investment in R&D with their chip manufacturer partner, though the cost may be an issue. Early engagement and co-optimization to provide a platform well suited for SoC-based mobile market is another role that foundries can play, as a traditional foundries model is struggling. And the foundries will have to become like integrated device manufacturing, providing design and process development under one roof. In supporting the 3D technology, TSMC is adding detected 300 mm R&D line to speed up 20 nanometer and 60 nanometer process development. Switching to FinFET production required a substantial investment, and TSMC's choice of the 3D technology pursuit will put pressure on other manufacturers to complete and choose the direction of 3D. Extend the Moore's law through innovative work and the research in finding cost-effective technology and manufacturing solution. Now in the conclusion. Intel pioneered the 3D transistor technology known as FinFET at the 22 nanometer process, which fueled the race towards 3D chip manufacture and scaling 40 nanometer chip and beyond. Intel, IBM, Global Foundries, TSMC, Samsung are among the leaders in the 3D technology. Mass production of 40 nanometer chips by leading world foundries and expected by 2014. The conclusion is key benefit of 3D transistor are that they use 40% less power and are 55 faster. Hybrid approach will allow foundries to catch up and replace the planar transistor with the 3D transistor. Early engagement and co-optimization by foundries is essential to the success and further development of this new technology. To reap full benefits of this new technology, traditionally foundries will have to become integrated device manufacturers, providing design and process development under one roof. Last three slides include reference used for this presentation. This concludes my presentation. Thank you.